Okay, hi VC. If you're here for homework help, go somewhere else. We're not doing any practice problems. This is sort of a passion project because I just want to show you why I think math is cool, and Taylor series are one of the big reasons for that. Um, so, you know, speaking broadly, I feel like one of the coolest things about math is you just take this really, really simple idea. In calculus, it's the idea of just finding the instantaneous rate of change of something. You take this one very, very simple idea and using just like careful thinking and logic and some cleverness, you come up with all of these insane extensions of this idea that like at surface level you would never guess were even possible. So specifically with derivatives, you know, bring with them the idea of a tangent line. Tangent line being it hits this point and it also has the same slope as the graph does at that point, like that. I'll call that x equals a because we're going to use this in a minute. The whole idea with the derivative is very close to that point, the graph looks like it's just a straight line. Like if you were to zoom in really far, it would just look like a straight line. So this tangent line, very close to this point, is a very nice approximation of the graph because it essentially matches it in the immediate vicinity of x equals a. But obviously, right, this thing deviates. It's not like it's a good approximation over here, or especially over here, of the actual value of the graph. Because, of course, this graph is not a straight line. This graph has some curvature to it. And that is obviously caused by a changing derivative. So it has a non-zero second derivative. And so what if we take this idea of the derivative and the tangent line and we extend it and we say, okay, why stop at tangent line? Why not also have its, graph something that hits here, has the same slope as here, and has the same second derivative as here? And that would look something like, I don't know, something like that. And that would be like a tangent quadratic or tangent parabola. And, obviously it still deviates, but theoretically very close to x equals a. It's going to be a better approximation. Okay, and then obviously why stop there, right? You could have a tangent cubic and a tangent quartic and a tangent quintic and, however many of these as you want. And if we're lucky, then maybe that will end up approximating the graph entirely, or even equaling the graph if we just keep adding terms. Now, obviously there's a lot of caveats to that. If we just keep adding terms, we might get infinity. So there's no guarantee, right? But that's our inquiry here, is we're just taking this idea of derivative and extending it and seeing if we can actually use some sort of tangent polynomial called Taylor polynomials, after the guy who came up with this idea. And we're gonna see how well can we approximate this graph. Of course, if we're asking how can we approximate it, we're also asking what is the error. So let's say I take my generic tangent function, which I'll just draw like maybe like this. That'll be our nth degree polynomial, which I'm going to call p of x. And obviously because it matches up with the derivatives up to nth degree and also the actual value of the graph, at that point it's going to be called centered at x equals a. So our question is, how bad is that approximation far away from a? Some finite distance later b, how bad is that approximation? So maybe b's over here somewhere. This is x equals b. How would I actually make sure that p of x has the same derivative as the graph at that point? Well, here is how you would do it. Obviously, if you had a tangent line, you would have p of x equal to f of a plus the derivative of f at a multiplied by x minus a, right? Okay, so what if I wanted to turn this into a tangent quadratic? Obviously we're going to need to have a second derivative term somewhere in there. Here's how we'll do that. We're going to add another term,
And this time it'll be the second derivative, right? We want the second derivative to match up at A.
And there's a few different ways you could go about this. I'll skip to the result, and I think it's not too hard to sort of reverse engineer this.
It's going to be x minus A squared over 2, right? That way,
If I take the derivative of this,
this guy goes away. Actually, let me just do it. dp dx equals df dx at A plus the second derivative of f at A. And notice this 2 is going to come out and cancel this 2 on the bottom. So you're just going to get x minus A there.
and so now you can see I differentiate this again, and I just get the second derivative of f at A. And so obviously the derivative of dp dx, the second derivative of p, evaluated at A would be the same as the derivative the second derivative of f evaluated at A.
And so then you keep going. If I wanted to make this a tangent cubic, I would have the third derivative at A, and this time I would have x minus A cubed, and then in the bottom I would have 3 times 2.
That way I differentiate, the 3 comes out, cancels the 3 below, differentiate it again, the 2 comes out, cancels the 2 below, etc.
By the way, that's 3 factorial. And so that's going to be the pattern in general. And so, you know, if you go until your nth degree term where you're going to stop, you're going to have nth degree derivative of f at A times x minus A to the nth power over n factorial.
Okay, so that's your polynomial that hits that point and has all the way up to nth degree derivatives in common with that point. So now the way we're going to phrase the question of, okay, how bad is the error here? All right, how bad of an approximation is this for any random x value b later? How far off is it from the actual function f? And the way we're going to phrase that question so that it's easier to answer is, well, how would I add a correction term on here such that when I plug in b, I actually get the value at b? That's going to be this. So, and we also don't want to mess up any of this stuff with all of the derivatives matching up to nth degree at A. So naively, you would just say, all right, well, I'm just going to add some constant m such that, you know, when I plug in b, I get f of b. But that's not going to work, right? Because if I just add an m, I'm going to take this tangent polynomial here, and it just shifts the whole thing up. And so obviously, I'm not hitting this point anymore, which I want to keep. So then your next idea would be, oh, well, I'll just add x minus a, right? That way I plug in x equals a, and this term just goes away. So that would mean that you still hit, at x equals a, you still hit the same value. But the problem is, you take the derivative of this and plug in a, you're gonna get df dx at a plus m, right? So then that messes up your first derivative. So what you gotta do is get this guy to be 0 for all of those derivatives up to nth degree, which means just raise it to a power n plus 1. That way, if I take, for example, the first derivative, this guy comes out in front, but then you plug in a, and then this whole term just goes to 0. It just goes away, and so you're still just left with, and obviously these terms would all go away as well, right? So you would just be left with df dx at a. Okay, so this is just, we're doing plus a constant m, and we're multiplying it by this, so that adding the constant m doesn't actually mess with any of our derivatives or the actual value of the function at a. So now the question is, what is m? By the way, think about how this would affect the graph. The graph is now 1 degree higher, so it's gonna, you know what, let me do this in purple just to show this, the shift. So it's 1 degree higher, so now it's gonna probably be curving down. And if this is x equals b, it's gonna go something like that, right?
That way because it's gonna hit A, it's gonna have all the same derivatives at A, and then it's gonna go up and back down through B, right? Because that's what we did. We added this M term so that it goes through B, or rather so that it intersects F at B. So then the question is, what does M need to be? Here's how we're gonna do that. Remember Rolls' theorem. If I have a function that starts at a value and ends at that same value some time later, and that function's derivative exists, which also implies that it's continuous, right? Differentiability implies continuity. So at some point, I'm gonna need to turn around and come back. So at some point in between here and here, my derivative needs to be 0. That's Rolls' theorem. Figuring out what M is just consists of absolutely abusing Rolls' theorem. First of all, let's consider, what we're gonna do is consider the difference between this corrected tangent polynomial and the actual graph. We're gonna consider the difference like right there. So that difference is gonna be, I'm gonna call that, I guess we'll call it E. Capital E, that's just gonna be the graph minus the actual, or minus the polynomial. This difference is gonna be 0 at A, and it's gonna be 0 at B. And we know that, so we're assuming, right, because we're using this derivative at least, we're assuming the graph is differentiable up to nth degree. And we're assuming that, well, obviously this Taylor polynomial is gonna be also differentiable up to nth degree. So, clearly this is gonna have a first derivative that exists. So by Rolls' theorem, we, because we start at the same value that we end at, sometime in the middle here, this difference, its derivative must be 0. So there's going to be some, I'm going to pull out some slight jargon here. This backwards E means there exists. So there exists some gamma 1, I'm going to call it, and that's between A and B, such that the derivative of this guy, of this difference between our graph and our approximation, is going to be 0. Our derivative of E with respect to x is going to be the derivative of f at x, and I'm just looking up here, I'm just differentiating term by term, minus the derivative of p of x, which is going to be, let's see, this goes away, that's going to be minus df dx at a, minus d squared f dx squared at a times x minus a, minus minus our nth degree term, but of course differentiated, it's the power rule. N comes out, n minus 1 at the top. The n at the top cancels out the n times n minus 1 times n minus 2 times etc. So you get n minus 1 times n minus 2 etc. n minus 1 factorial minus, and then we power rule this last term, n plus 1 times m times x minus a to the n. All right, here's why I went through all of that. Notice, if I were to take the second derivative of our difference, and specifically if I did that at x equals a, I would get, let's see, these two terms would go away, this would be a constant term, all of these other terms have an x minus a in them, so they would all go to 0, so I would just be left with the second derivative of f at a, which obviously the second derivative of f at a is the second derivative of f at a. So I would get second derivative at a minus second derivative at a, which is 0. Right? And you can see how the same would hold for the third derivative and the fourth derivative and all the way up to the nth degree derivative. Our kth degree derivative of e at a is going to be 0 for all k in between 0 and n. Our 0th derivative, of course, would just be actually the function itself. Okay, and so here's why we care about that. We just said that somewhere between a and b, our derivative of this difference is going to be 0. And we know that our derivative of this difference is also 0, our first derivative I'm going to talk about, right? Because that's in between 0 and n. 1 is in between 0 and n. So our first derivative is also 0.
at x equals a. Well then, if our first derivative is 0 here and 0 here, and obviously it's continuous because we have a ton of derivatives past first degree, then Rolle's theorem, right? There has to be some point where the derivative of the first derivative is 0 in between a and gamma 1. So then there exists some gamma 2 in between a and gamma 1, such that the second derivative, the derivative of the derivative at gamma 2, is equal to 0. Well then, if the second derivative is continuous and equals 0 here and equals 0 at a, well then in between a and here, there must be some point where the derivative of the second derivative, which is the third derivative, equals 0. And you see what I'm talking about? We're abusing Rolle's theorem. So we can do that all the way down to our nth degree. So there exists some gamma n in between a and whatever, gamma n minus 1, such that the nth degree derivative of our difference at gamma n equals 0. And now here's what we're going to do. We're going to assume that this function is differentiable one more time, past nth degree. We're going to assume that f is derivative, f's nth plus 1 derivative exists. Here's what that does for us. It lets us do this one more time. We know that our nth derivative is going to be 0 at a and sometime later at gamma sub n. And so there should exist some, and I'm just going to call this one gamma because it's extra important. There exists some gamma in between a and gamma n such that our n plus 1 derivative of x, or of e, at gamma equals 0. What is our n plus 1 derivative of e? It's going to be the n plus 1 derivative of f, and we're plugging in gamma, minus, and then it's going to be the n plus 1th derivative of p. This is nth power, everything else is less than nth power, so all of this goes to 0, and this becomes power rule out, n plus 1, and then n, and then right, all the way down to where we just have power ruling out the 1, so we just get m, and then out front we have n plus 1 times n minus 1 times n minus 2, all the way down to 1, which is n plus 1 factorial. So our n plus 1th degree derivative here is going to be just a constant, so I don't need to plug in, obviously, because it's a constant, and it's going to be n plus 1 factorial times m, and that is going to be 0 for whatever this gamma is in between a and gamma sub n. Now, also notice gamma sub n is in between a and gamma sub n minus 1, which is in between, and gamma sub n minus 1 is in between a and gamma sub 1, and gamma sub 1 is in between a and b. And so all of that to say that if gamma is in between a and gamma sub n, then it's also going to be in between a and b. So there's some gamma between a and b such that this equals 0, and of course now we can literally just rearrange and solve for m. M equals the n plus 1th degree derivative of f at some gamma in between a and b over n plus 1 factorial. And there is your proof. So that's what our coefficient needs to be here in order for this correction term to work and for us to properly hit f of b. Remember at the beginning, what if we just keep adding terms? Can I get this correction term that needs to be added? Can I get that to be 0? Because if I can, then I can just add infinitely many terms with no error. I can approximate this whole graph, because remember, b can be anything. So I can approximate this whole graph with 0 error if I just keep adding terms, if this goes to 0. Well, if this goes to 0, really. Okay. Ever wondered how to calculate sine of any angle? We're about to. Because guess what? Let f be sine, then m times x minus a to the n plus 1. That's going to be equal to, it's going to be, so we know that the derivative of sine is either going to be cosine like the nth degree or n plus 1th degree derivative of sine is going to be sine or cosine or negative cosine, right? And the biggest and smallest of those guys can be is 1 and -1, right? You plug in any number. So whatever gamma is, it's going to be something in between -1 and 1 over n plus 1 factorial multiplied by x minus a to the n plus 1. Thus, for any number b, if we take the limit as n goes to infinity here, I don't care what b minus a is, there's gonna get a point where n is so big that this denominator is so much more huge than this numerator that we're going to approach 0. So for any b, the limit as n goes to infinity of m times x minus a to the n plus 1 equals, or sorry, times b minus a to the n plus 1 equals 0. That's assuming f of x equals sine of x. So what does that mean? It means our error goes to 0 as you keep adding terms, which means that I can just plug and chug. Just this, but then keep going, don't stop it in. Therefore, sine of x equals, all right, let's see here. We're gonna do this, we're gonna say a equals 0. So we're gonna expand around, we're gonna center at 0. Sine of 0 is 0. So don't need to worry about this term. Derivative of sine is cosine. Cosine of 0 is 1. We're gonna multiply that by x minus 0, which is just x. So that's just x. And then the second derivative of sine is negative sine. That's going to be 0 at 0. Third derivative is going to be negative cosine. That at 0 is -1. -1 multiplied by x cubed over 3 factorial is what we're going to add on next. So minus x cubed over 3 factorial. And I think you're starting to see the pattern. All of the even terms are going to go to 0 because it's going to be sine of 0. All of the odd terms are going to alternate between positive and -1 for these derivative coefficients. And so what we're going to end up with is plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial minus, and then it just keeps going. I can repeat this process over again for cosine, right? It's the exact same deal. Whatever this is going to be, its derivative is going to look, or whatever cosine is, it doesn't matter what n is, it's going to be something like this. So clearly our error goes to 0 just for the exact same reason as sine's error went to 0. And so that implies that cosine of x is equal to, and now, so this is the different part, is cosine of 0 is 1. Derivative of cosine is sine. So we're going to get 0 for that next term. Second derivative is negative cosine. Negative cosine of 0 is -1. And then we've got x squared over 2, which is the same as 2 factorial. And then I think you can see all the odd terms cancel and all the even terms become alternating positive and negative. X to the whatever over whatever factorial. So x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus, and so on. Okay, what about e to the x? E to the x has very nice properties, right? Its derivative is always going to be the same. Let's say f equals e to the x. Then m times x minus, or times b minus a to the n plus 1 equals e to the something, right? And our derivative is going to be e to the x always. And we plug in gamma, so it's going to be e to the power of something over n plus 1 factorial multiplied by b minus a to the n plus 1. And again, n plus 1 factorial, there comes a point where if it gets big enough, this becomes practically 0, right? N plus 1 factorial is going to end up being way more huge than this guy is. And this is just a constant, so we don't have to worry about it. So this whole thing goes to 0 as n goes to infinity. Therefore, we can also write a Taylor series. By the way, that's what these are called. Once it becomes an infinite sum, it's a Taylor series. Therefore, e to the x is going to be, and then let's see. So we're going to do this centered at 0 again. e to the 0 is 1. And then it's going to be plus e to the derivative of e to the x is e to the x, e to the 0 is 1. So again, it's 1 times x plus 1 times x squared over 2 factorial, why not, plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on forever. If you'll notice, like we've got x cubed over 3 factorial, x cubed over 3 factorial, x. It's kind of looking like some weird combination of these, except these guys have minuses and this is all pluses. So I wonder if we could modify one of these guys in some way to get them to look like each other. Here's how we do that. Remember I? For those of you who don't remember I equals the square root of -1. It's called an imaginary number. I is called the imaginary unit because it's like the one of imaginary numbers, if that makes sense. What if we look at e to the ix? Well then I'm just gonna plug in ix for all of these. So I'm just gonna get 1 plus ix, and then ix squared is gonna be -x squared, so it's gonna be minus x squared over 2 factorial. It's gonna be minus I times x cubed over 3 factorial plus x to the 4th over 4 factorial plus I x to the 5th over 5 factorial minus, and we keep going. But now notice, we've got I times x. We've got negative I times x cubed over 3 factorial. Positive I times x to the 5th over 5 factorial. That's looking a lot like this multiplied by I. We've got 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. That's looking like this. So you know what this is? This is cosine x plus I times sine of x. E to the I pi plus 1 equals 0. Which is kind of cool because we just took 3 constants that have nothing to do with each other, e, I, and pi, and well, 1 and 0 are also constants that have mostly nothing to do with each other. We just sort of threw them together and we got this. We just related all of these fun little famous constants in math using one equation. I mean, that's pretty cool to see it all come together like that. And also, of course, to be able to start with the idea of just instantaneous rate of change, and all of this comes from that, and then you can suddenly find sine and cosine of any angle. I mean, like, to me, that's pretty freaking cool. Hope you agree.